back to your one and only favorite YouTube channel, Tomachang Tutorial. Myself, Kishan Kulung, and today we are ready to go for a new topic, and that is Lother-Meyer's curve. Okay, we are going to discuss about Lother-Meyer's curve in this video. We have already completed Dobrynier's law of triad and Newland's law of octaves in our previous videos, so please find the links below in the description and watch those videos. Okay, now let's move on to today's topic, Lother-Meyer's curve. Lothar Meyer was a German scientist. Lothar Meyer was a German scientist. In the year 1864, he conducted an experiment and found the relation between atomic mass and atomic volume of elements, of different elements. Let us say different elements. Okay, of different elements. Lothar Meyer conducted an experiment in the year 1864 and found the relation between atomic mass and atomic volume of different elements. Okay, and he plotted this in his graph. Okay, he plotted this in his graph. Atomic mass he plotted in x-axis and atomic volume in y-axis. When atomic mass versus atomic volume was plotted, his graph looked somewhat like this. Okay, this is not the exact graph of Lothar Meyer. This is only for demonstration. I'm just showing you. It looked somewhat like this. When atomic mass versus atomic volume, when atomic mass versus atomic volume was plotted, the graph thus obtained looked somewhat like this, and this curve is popularly known as Lother-Meyer's curve. Okay, I hope you got this. Now, before going to the depth of Lother-Meyer's curve, let us first understand the relation between mass and volume. We know this, isn't it? The relation between mass and volume of any substance. Mass of a substance is directly proportional to its volume, isn't it? Which means when you increase the mass of the substance, the volume of the substance also increases simultaneously. And if you decrease the mass of the substance, then the volume of the substance also decreases simultaneously, isn't it? This relation is true for every physical substance existing in this universe. Okay, let me give you an example to prove this. Okay, we have a container here, and in this container we have 5 kg of rice. Okay, we have 5 kg of rice. 5 kg of rice occupied this much space. We can say this is the volume of 5 kg of rice, isn't it? 5 kg of rice occupied this much space, means this is the volume of 5 kg of rice. Now we put extra 2 kg of rice. Okay, we put extra 2 kg of rice. This 2 kg of rice also requires some space, isn't it? Now this is the new volume. This is the space occupied by 2 kg of rice. What do we understand from this? When the mass of the substance, or when the mass of the rice was 5 kg, the volume occupied was this much. When we increase the mass of the rice to 7 kg, the volume occupied is this much, isn't it? This proves that when we increase the mass of the substance, then volume of the substance also increases simultaneously. And the same, when we decrease the mass of the substance, the volume of the substance also decreases simultaneously. I hope you understood this. Okay, from this relation only the formula of density comes, isn't it? Mass, when we replace the sign of variation with equal to sign, we need to introduce a constant, that is k, into volume, isn't it? Where k is constant, or you can say variation constant. Variation constant. K is variation constant. Got a point? Or bring this volume to the denominator by cross multiplication. Mass upon volume equal to K, isn't it? This K is known as density. This K is known as density. We got the formula of density. Density equals to mass upon volume. The formula of density, mass upon volume, is actually deduced from this relation. Mass is directly proportional to volume. Okay, got a point? This relation holds true for every physical substance existing in this universe. Okay, when we increase the mass, volume of the substance increases. And if we plot graph for this, it will look somewhat like this. Mass of 5 kg of rice, don't say 5 kg of rice, mass of any substance versus volume of the substance. Okay, volume of the substance. If we plot the graph, then the graph would look like this, isn't it? When the mass of the substance is 0, the volume is also 0. When you increase the mass here, volume becomes something. Suppose mass is 1, volume is 1. When you increase the mass to 2, volume also increases 2, isn't it? When you increase mass 3, volume also increases 3. When you increase mass 4, volume increases 4. On increasing the mass, volume also increases simultaneously. When you increase the mass, volume also increases, isn't it? But this is not what Lothar Meyer got when he experimented atomic volume versus atomic mass. Okay, let's see his experiment now. Not experiment, his curve. Okay, let us forget this all this thing and let us see Lothar Meyer's curve. Lothar Meyer's curve. I am drawing this just for demonstration. Please do not understand this is the exact graph of Lothar Meyer. This is not the exact graph of Lothar Meyer. I am just drawing this for demonstration. Okay, it somewhat resembles like this. Atomic mass was plotted in x-axis, isn't it? Atomic mass. If you move this side, atomic mass increases, and atomic volume in y-axis, which means if you move upward, atomic volume increases. Now when he plotted atomic mass versus atomic volume, his curve looked like this. Okay, on increasing the atomic mass, please listen to me. Okay, on increasing the atomic mass, atomic volume should constantly increase for normal substance, isn't it? For normal substance, when you increase the when you increase the mass of the substance, volume of the substance also increases. But in case of atom, when you increase the atomic mass, volume of the substance increases. It's increasing, isn't it? It's going upward, means it's increasing. But after reaching a certain point, after reaching this peak, okay, when you increase the atomic mass, the volume starts decreasing. Atomic volume starts decreasing. Again, after reaching the lower point, when you increase the atomic mass, now the atomic volume also starts increasing again. And after reaching this fixed point, when you are constantly increasing atomic mass, isn't it? Atomic mass is constantly being increased. So on increasing atomic mass, atomic volume again starts decreasing. And after reaching this point, you are constantly increasing atomic mass. Atomic mass is constantly being increased. Again, atomic volume starts increasing. Atomic mass starts increasing. And after reaching this point, you are constantly increasing atomic mass, but atomic volume after reaching this point starts decreasing again. And again the same pattern follows. Got our point? Atomic volume does not keep on increasing like this. It increases, and after reaching a certain point, again it starts decreasing. Again it starts increasing, again it starts decreasing. Increasing, decreasing, increasing, decreasing, isn't it? That is the way how it looks. Okay, but when we look at the peaks, oh, this peak is smaller. when we look at the peak, okay, when we look at the peak, when we look at the peaks, this peak is lower than this and this peak is lower than this, isn't it? This means atomic volume is increasing, atomic volume is increasing with the increasing atomic mass, but with fluctuations, isn't it? Overall atomic volume is increased. This lower fixed point is at lower point than this, and this is at higher point, isn't it? Atomic volume is constantly increasing. You see atomic volume is increasing but with fluctuations, okay? It increases to a certain level and again decreases. It increases to a certain level and again decreases. It increases to a certain level and again decreases, which means overall the atomic volume is increased but with fluctuations. Fluctuations means with periodicity, isn't it? Okay. Now, what Lothar Meyer observed is elements, when atomic mass of elements and atomic volume of elements were plotted, alkali metals, lithium, sodium, potassium, rubidium, cesium, etc. occupied the peaks of the curve. Okay, alkali metals like lithium, sodium, potassium occupied the peaks of the curve, okay, periodically, isn't it? Lithium, and then again comes sodium, and then again comes potassium. The peaks of the curve are occupied by the alkali metals, and alkali metals are the most electropositive. They are the most electropositive elements, okay? Alkali metals are called the most electropositive elements because they have the greatest tendency to lose electrons, okay? Number 2, halogens, fluorine, chlorine, bromine, iodine, etc. were found in the ascending portion of the peaks, portion of the curve, okay, of the curve. Are you getting me? Halogens, fluorine, chlorine, bromine, iodine, etc. were found in the ascending portion of the curve. Ascending portion means this, isn't it? Fluorine, chlorine, bromine, and if this was a curve, then this is iodine. Ascending portion of the curve, in the every ascending portion of the curve, the halogens were found. Halogens are the most electronegative elements. Most electronegative elements. Okay? Why they are called the most electronegative elements? Because they have the greatest tendency to gain electrons. So they are called the most electronegative elements. Let me erase the upper part, okay? To continue. Alkaline earth metals. Beryllium, magnesium, calcium, strontium, and etc. were found in the descending portion of the curve. Okay. Alkaline earth metals like beryllium, magnesium, calcium, strontium, barium. You can write barium also here. Strontium, barium, etc. were found in the descending portion of the curve. Descending means this, isn't it? Descending portion of the curve. Beryllium, magnesium, calcium, etc. were found in the descending portion of the curve. Okay, and they are called alkaline earth metals. They are little less electropositive than alkali metals. Okay, alkaline earth metals are little less electropositive than alkali metals. They also lose electron, but the tendency to lose electron is lesser than alkali metals. Okay. Number 4, metalloids. Example: arsenic, silicon, boron, germanium, tellurium, polonium, etc. and transition metals, transition elements. They are also called transition metals. Transition elements example: gold, silver, cobalt, nickel, etc. were found in the bottom portion of the curve. Okay, we will learn about these transition elements and all metalloids in the modern periodic table, but right now I am giving examples. Okay, metalloids like arsenic, silicon, boron, germanium, tellurium, polonium, etc. and transition elements like gold, silver, cobalt, nickel, etc. were found in the bottom portion of the curve. Means all these metalloids and transition elements were found in the bottom portion of the curve. Okay, this means elements having similar properties are found in the same side of the curve, isn't it? Fluorine, chlorine, bromine, they have similar properties. They are all electronegative elements, are found in the ascending portion of the curve. And highly electropositive elements like lithium, sodium, potassium are found in the peaks of the curve. And alkaline earth metals are found in the descending portion of the curve. Similarly, metalloids and transition elements are found in the bottom portion of the curve. This means this curve gives us the idea of periodicity of elements, isn't it? Elements having same properties are found in the same portion of the curve, isn't it? Got my point? So from this graph, Lothar Meyer gave us or put forward his law, and his law states that physical properties of elements, are the periodic function of their atomic masses or atomic weights. Okay, physical properties of the elements are the periodic function of their atomic masses. Okay, means on increasing atomic masses, atoms having or the elements having same properties are found, isn't it? Fluorine, chlorine, bromine are found in the same side or the ascending side of the curve. Lithium, sodium, potassium are found in the peaks of the curve, and metalloids and transition elements are found in the bottom portion of the curve. Similarly, alkaline earth metals like beryllium, magnesium, calcium, etc. are found in the descending portion of the curve. So this gives us the idea of periodicity of the elements, isn't it? I hope you understood the Lothar Meyer's curve. Thank you so much for watching this video, and Stay blessed, stay happy, and please don't forget to subscribe and click the bell icon to get notifications for more video uploads. Thank you.